work that we've done over the last couple of years. The general theme is doing importance sampling in high dimensions and using hashing in order to do this. So I want to give you an overview of some of the results that we've obtained, give you a flavor of some of the techniques, and all the various ways in which, all the various kinds of problems that we've applied them to. Some of you might have seen some of this before. In fact, I've actually spoken here at Simon's at least a couple of times on two different things that I'll actually talk about in this talk. So if you feel like you've seen this before, you're probably right. But hopefully there'll be something new in the talk for you. Okay, so let me start with a generic problem. And this will be the basis for much of my talk. Okay. So what's the setting? The setting is we're given a bunch of points in d-dimensional space. Think of d as very large. There's some function k. We'll call it a kernel function. It takes a pair of points and outputs a number, positive quantity. And we have a query point q. What we'd like to do is we'd like to go over the data set, compute this pairwise function k pq for the query q, and all the points in the data set, sum them up and average over the data set. Okay? So, given this data set, it's easy to compute this, linear time, just make a pass over the data. The main question is, if you wanted to evaluate this, and we want to evaluate this not for one query, but for multiple queries, is there some way in which we could pre-process the data set so as to be able to answer this question quickly? Okay, at query time. So what kind of data structure would we need in order to pre-process this data so as to answer such queries quickly? Okay, so that's going to be the basic question. I'm not going to spend very much time on motivating the problem, but let me just say briefly that this kind of question, for example, arises in non-parametric statistics, where you have a data set, it comes from some unknown distribution, you'd like to figure out what this distribution is. This is one class of non-parametric method that's used to figure out what this distribution is. If you think about this kernel function, for example, one kind of kernel function that people use is the Gaussian function. This amounts to saying that let's take the empirical distribution, let's smear it a little bit, and let's compute the average of this smeared distribution. Okay? And so people care about this kind of calculation in this setting, but also in a number of other settings. Okay, so this is the basic question. So there are a few different questions that you could ask. One is this data structure problem that I just mentioned. If you wanted to approximate this quantity, let's say this average is mu, can you approximate this to within 1 plus minus epsilon, and how do you do it? What's the data structure? Okay. There's also this another problem that people have considered, which is sort of this batch offline problem. You're given a bunch of points p and q beforehand. Imagine building this kernel matrix Kij, which has the kernel values for pi and qj. That should be j. And now, given a vector w, you'd like to approximate the product of k times w. This is another problem that people care about. Yet another problem might be you want to sum up all of the entries of this kernel matrix and average over all the points. Okay, how quickly can you do this? Okay, so I'll mostly focus on this data structure problem. Okay. All right. So one question is what is this kernel function? And I'll give you examples of kernel functions people use. One commonly used kernel function is the Gaussian function. There's also the exponential function. You can look at functions which look like exponential in inner products, and you can put different kinds of functions over here in the exponent, all functions of the inner product. There are other functions, the logistic function. There are also a bunch of functions here. These are all functions that people do care about and use. And as we'll see, actually, how hard this problem is, the resources that we need to evaluate this will actually depend on the kernel function. Okay, so one theme in the talk will be that we can do better if we know something about the kernel, this kernel function that we care about. Okay. So let me tell you a few results that are known for these kinds of problems. So before I state the results, let's do some normalization. Okay. So I said that we have this kernel function, and we want to average this kernel function over all the values of the data, over all the data points. Let's just normalize so all our kernel function values are between 0 and 1. Okay, and let mu be the average. Mu is this quantity that we're trying to compute. So one natural approach is to just do random sampling. Okay, if instead of actually summing up all the data set, if you just random sample the data set, how many samples you need to get a 1 plus epsilon approximation? Well, it's pretty easy to calculate. The number of samples that you need, first of all, the dependence on epsilon is 1 over epsilon squared. Okay, and the dependence on mu is going to be 1 over mu. Okay, the 1 over mu dependence is pretty easy to see. The hard case is where you're getting mu contribution because exactly mu fraction of the data gives you 1, and the rest have contribution 0. So even for a random sample to even hit something that gives you non-zero contribution, you need to sample 1 over mu times. The random sample needs so much. Okay. These kinds of questions have been studied in low dimensions by Greengard and Strain, Greengard and his collaborators. There's something called the fast Gauss transform that allows you to compute this kind of quantity for all pairs. And if you use those methods, the scaling is exponential in dimension. Okay, so on one hand, the dependence is logarithmic in 1 over mu. Okay, but unfortunately, these methods behave very badly as the dimension increases. They're exponential in the dimension. And very roughly speaking, these methods are based on hierarchical space partitions and doing something clever with the distribution of data with respect to these hierarchical space partitions, but unfortunately they scale very badly with dimension.
Moses?
Yeah.
So the first method you mentioned does not require pre-processing, but I guess this fast Gauss transform does require pre-processing.
The first one doesn't require pre-process. Yeah. So it's very attractive.
But this thing does require like some space partitioning.
Yeah. So technically, this this is trying to compute the following quantity. Okay, it's you have n points. You're computing for each of these n points the net effect of the remainder of the data set on that point. So you're not actually doing any pre-processing. You can do all of this at query time. It's just that you have a batch of n queries at the same time, and you want to evaluate all of them. That's the way in which these things are phrased. Although the way I've explained this, I've sort of said this is sort of the
work per point.
The work per point, yeah, exactly. Okay. All right. There are a bunch of results by Jeff Phillips and his collaborators that give very interesting guarantees. They get additive epsilon approximations. The guarantees are sort of stronger because there are also this sort of for all versus for each guarantees. And these guarantees hold for all queries simultaneously. And what they get is very interesting dependence. They basically say that you can get a core set of this size, so you can get an additive epsilon approximation. And in our language, if you want to get a multiplicative 1 plus epsilon approximation, the dependence would be so much. Okay, so again, the dependence on mu is 1 over mu. Okay. So one of the main results I want to tell you about is by using hashing, by using estimators that are based on hashing, we can actually improve the dependence on mu from 1 over mu to 1 over square root mu. Okay, I want to tell you about that. This was obtained in a paper of mine with Paris Similakis, who's here in the audience. And we managed to do this for some of the kernels that I mentioned above, the Gaussian kernel, the exponential kernel, and the t-student kernel. Okay. Now, I'll spend some time explaining how this works. This is going to be the basis for everything I say later. In later work, we also managed to generalize these ideas to pairwise functions which look like exponential in some function of the inner product. Okay? And roughly speaking, we get the same kind of dependence. Now there's going to be some dependence on what this function phi is. Okay, I'll tell you a little bit about that as well. And finally, I want to talk about whether we actually do need this polynomial dependence on mu. Okay, so all of these results are going to have dependence on mu, which is 1 over square root mu. So which means that when mu is really tiny, the query time is very large. Okay. Do we actually need this dependence on mu? Could we get something which has a better dependence on mu? And I'll answer this question in the latter half of the talk. Okay.
So why doesn't the fast Gauss transform already answer the question?
Well, because I want to avoid this exponential dependence on d.
Oh, okay.
So not only do I want to, okay, so I want to not get a polynomial dependence on mu without having to pay this exponential cost. That's the question. Okay. Other questions?
Is it possible to combine the hashing-based estimator with the fast Gauss transform in the lower dimension?
I don't know, actually. Interesting question. I don't know if it's possible. Okay. Other questions?
What sort of approximation guarantee do you get in terms of epsilon?
So all of these are trying to get a 1 plus epsilon approximation. That was the approximation guarantee. Okay,
So it's not additive. So it's not additive.
It's not additive. It's a multiplicative 1 plus epsilon. Okay. All right. So let me tell you, I'll start building up the sequence of ideas by starting with this work. I'll talk a little bit about this work, and then finally I'll talk about how one can break this polynomial dependence on mu if you know some additional information about your kernels. Okay. So so this was the paper where we started working about on these ideas in Fox 2017. Okay. So here's the problem that we're going to solve. Actually, this is not exactly the problem I phrased, but if you can solve this problem, then you can solve the problem of estimating kernel density within 1 plus epsilon. So let's say you just wanted to distinguish between two cases. Either the kernel density is less than 1 minus epsilon times mu, or it's bigger than 1 plus epsilon times mu. Okay. If you had a procedure to do this, then you can do binary search and figure out you can get a good approximation to what the kernel density is. Okay, so this is our problem. One other technical thing. We're going to say that we're interested in solving this problem so long as the kernel density is within the range tau to 1. Okay. So we're going to assume that our kernel density is in this range, and our data structure will be built around tau. Tau will be parameter to our data structure. Okay. So if you want to solve this problem, we can do this with query time which is 1 over root mu. Now I'm going to ignore this. Whenever I have this kind of query time, I'm always going to have 1 over epsilon squared dependence, so I'm going to not mention it. So I'm going to get query time which is 1 over square root mu. And the size of the data structure is going to be n times 1 over square root tau. Okay? Tau, if you remember, was this lower bound on mu. Okay, so that's the main result. All right? Okay, and we do this for, as I said, the Gaussian kernel, for the exponential kernel, and also for this kernel that's called the generalized t-student kernel. Okay. So this, as I said before, random sampling needs query time 1 over mu. This gives you a square root mu improvement over random sampling. Okay. Of course, you pay a huge cost, which is random sampling is very easy. You need no pre-processing. This one, on the other hand, you do need to do some pre-processing beforehand. Okay. So one thing that might be a little strange about this result is that mu is the quantity that we're trying to estimate, but I'm expressing my query time as a function of mu, which is exactly this quantity that we're trying to estimate. Okay. Actually, what's going to happen is that our algorithm is going to adaptively estimate mu, exactly by doing this binary search like procedure. Okay. So when it terminates, the guarantee is that the amount of time that it takes is 1 over square root. Okay. All right. So let me explain the main idea behind this first piece of work. Let's try to think about a more simple setting. Okay. So you have your data set consisting of points xi. There's a weight attached to every element of the data set, right? It's the weight is just the kernel value, right? It's the kernel value between x and xi. And what we want to do is approximate the sum or the average of these kernel values. In other words, we want to approximate the sum of these wi's. Okay? Now, what does random sampling do? Random sampling picks a random element amongst these and uses the averages a bunch of these random values. Okay? Now the problem is that why does random sampling do badly? The case where random sampling does badly is exactly where a small number of weights have very large contribution. Okay? If you could sort of sample in a more intelligent way, so you can do well in the setting where a small number of points have very large contribution, then you could beat random sampling. Okay? And that's the main idea. Okay? In our case, what is this quantity that we're trying to estimate? We're trying to estimate the sum of the kernel values. Which are the kernel values that are likely to be large? Well, they're exactly the points that are near the query. Okay? So intuitively, if we could build a sampler which samples points that are near the query with higher probability than points that are further away, we should be able to do better, right? And that's exactly what we do. Okay, so let me tell you a little bit about importance sampling. Suppose instead of uniform sampling, we had a bias sampler. Okay, so we had some black box way of sampling the data set so that I is returned with probability Q of I. Okay. Now it's possible to, just like with random sampling, it's possible to design an unbiased estimator for this biased sampling procedure. What we do is we sample element I, and then we look at the weight Wi, we divide it by the probability that you sample the element Qi. Okay? And now this is an unbiased estimator. Okay? This is a standard importance sampling. The variance of this estimator is going to be summation of Wi squared by Qi. Now you could ask, how should you set your sampling probabilities so as to get a low variance estimator? Well, the best choice, the ideal choice of sampling probabilities is to sample elements directly proportional to their weights. Okay, so this would actually minimize the variance. But here's the challenge. In our setting, the weights are these kernel values. Okay, we don't know them a priori, and besides, not only do we not know them a priori, they're not fixed for the data set. They're query dependent. Right? If the query is in a particular region, you're gonna have to you prefer to sample points that are in that region. If the query is in another region, you prefer to sample points in another region, and so on. Okay? So somehow we have to design a sampler which is inherently query dependent. Okay? And that's exactly what locality sensitive hashing does for us. Okay? So what is locality sensitive hashing? Intuitively, it's a way to randomly partition the data in such a way that points that are nearby are likely to fall into the same piece of the partition, and points that are further away are relatively unlikely to fall in the same part of the partition. Okay? So this is a very influential technique to build what are called nearest neighbor search data structures. How does this technique work? Well, you typically have some family of hash functions. Okay? So given a point, this computes a value. There's a distribution of these hash functions. Now, there's also a collision probability. So given points x and y, you can look at the probability that x and y land up in the same bucket if you pick a random hash function from this family. Okay? And typically this collision probability x and y is going to be some function of the distance between x and y. Okay? You expect that points that are nearby are more likely to collide, land in the same hash bucket, than points that are further away. You can actually characterize this for a particular family of hash functions. There's a function that tells you exactly how the collision probability behaves as a function of the distance. Okay? All right, so that's what locality sensitive hashing gives us. And the key idea, as I said, is to think of locality sensitive hashing as a way to implement importance sampling for our purpose. Okay? So how does this actually work? Okay, so what we're going to do is we're going to pick a family of hash functions. with some collision probability. Okay, we're going to evaluate these hash functions h1 to hm on our data set. Okay, and now what we're going to do is we're going to look at the query. Right? Let's say the query is x. We're going to look at all the points of the data set that have the same hash value as the query, that land up in the same hash bucket as the query. From amongst these points, we're going to sample a random point. Okay? So we evaluate the hash function on the data set, evaluate the hash function on the query, look at everybody who collides with the query, and sample a random element from
Is
that.
that necessarily efficient to find out everybody that collides?
The evaluation on the data set is done a priori, is pre-processing. So we have a hash table, everything's already placed into a hash table. The query maps to the hash table, and now we just look at an element, right? So even though I've expressed it like that, much of this is done as part of pre-processing. Okay. Other questions?
When you just sample one, is that like further speed up, or how does it compare to just evaluating everything in the same bucket?
Everything in the same bucket. So one thing is I don't have a handle over how many elements fall in the same bucket. Okay, it could be that a lot of the data set falls in the same bucket, and I might spend a lot of time. So for efficiency reasons, I'm going to look at only one element. It would simplify the calculations a little bit if I could actually look at the entire bucket and look at its contribution. But I'm going to look at only one element. Yeah.
So are you guaranteed to have something in the same bucket?
Are you guaranteed? No. And if you don't get something, then you return 0. Okay. So if you have something in the bucket, then you look at the value of the kernel, right? Now remember, the standard importance sampling, you got to take the value that you get, divided by the probability of having sampled this element. Okay. So what's the probability of having sampled this element? Two things need to happen. One is this element needs to land in the same hash bucket as the query. Well, that's given by this probability. But then, of the many elements that landed up in the same bucket as this query, this particular element better be picked. So that probability is divided by the size of the hash bucket. Okay. So this is the value of our estimator. It's exactly what importance sampling gives you. Right? Except this is some sort of weird importance sampling because it's based on this hash table. There's a weird dependency between these probabilities that's introduced by this hash table. Okay, so this is an unbiased estimator, not very hard to show, and the main technical contribution is really analyzing this, bounding the variance of this estimator. Okay, so earlier I told you what's the variance for importance sampling. It was just sum of the weights squared divided by the probabilities, right? In this case, it turns out that the variance of this estimator is exactly the same thing, but then there's this pesky term here. Okay, and this pesky term says it's the expected size of the hash bucket containing the query, given that I map to this particular hash bucket. Okay, so this is the.
What's the meaning of PI? What's the meaning of PI?
PI is so you have the ith data point. PI is the probability that the ith data point mapped to the same hash bucket as the query. That's what PI is. Okay. So this seems like a really unwieldy thing to analyze. In some sense, it depends on the hash function in some weird way. It depends on the structure of the data set in some way, right? Because how do you talk about the sizes of hash buckets and so on? One of the key ideas in simplifying this analysis is that, in some sense, the worst case data sets, the data sets that maximize the variance, are those that have their support only on 2 points. So somehow, relative to the query, all of the data set sits either at one distance threshold or another distance threshold. Okay, and those are exactly the data sets that give you the worst value for this variance. Once you have this insight, it really makes the analysis much simpler. Okay, so this quantity here, let me just tell you what's actually involved in the analysis. I won't give you the analysis, but tell you what are the key facts that I use. This thing, the expected size of the hash bucket, is just the sum of the collision probabilities, right? What's the probability that I and j both belong to the hash bucket divided by pi. Okay, that's what this is. And then the only other thing that we use in the analysis is that the probability that both I and j belong to the hash bucket is at most the minimum of pi and pj. Okay, so this is a very simple naive bound, but that's really all we use in the analysis. So using these facts, you can actually show that these are the only facts that you use. You can show that this expression is maximized for data sets that have a very simple simple structure. They have their support on only two different distances. Okay. So in our analysis, one thing that that gives you interesting bounds is to look for hash functions where the collision probability scales somehow as a function of this kernel that you wanted, right? As you expect, earlier we said if you wanted to do importance sampling, the probability of sampling an element should be directly proportional to its weight, right? If you use that intuition, it would seem that the natural thing to do would be to find a hash function whose collision probability was exactly equal to the kernel value. Okay? Turns out that that's not quite the case. The fact that this is not pure importance sampling, we're sampling based on a hash function and the hash bucket and so on and so forth. Things are a little more complicated. But it's still useful to think about a hash function whose collision probability somehow is controlled by the kernel. Behaves like the kernel in some sense. Okay? So we look for a hash function whose collision probability behaves like the kernel raised to the power of beta.
Yeah. Is the issue that there may not exist an LSH with beta equals 1, or is it the case that you actually prefer beta not to be 1?
It's the latter. We prefer beta not equal to 1. Okay. Beta equals 1 is not the optimal choice. Okay, that's what happens. So it turns out that if you compute the variance of, so if you try to find a hash function whose collision probability behaves like the kernel value raised to the power of beta, okay, as I said, the worst case is this 2-point data set where all the points are either at one distance, let's say distance 0, or another distance, let's say distance so much where the contribution is mu. Turns out that the best value of beta is half. Okay, so I won't actually go through the analysis, but turns out that in our analysis, the best choice for collision probability is proportional to the kernel value raised to the power of half. Okay? And we can actually achieve this for all of these kernels that I mentioned before. For the Gaussian kernel, for the exponential kernel, and for the t-student kernel. We can actually achieve this. And this is by using standard LSH functions. So for the Gaussian, we use a locality sensitive hash function due to Andonian indic, something called the ball carving hash function. For these, we use another one which was done earlier for Euclidean data sets. Okay. All right. So good. What was the main insight? The main insight was that if you know if you have a kernel function, if you can find a locality sensitive hash function which somehow matches the collision probability somehow matches the kernel, then you get this 1 over square root mu result. All right. Questions? And we can do this for these particular kernel values, which are interesting kernels that people do care about. Yes.
Do you know what are some kernel functions when random sampling is actually optimal, or how do they look like, such kernel functions or not?
What are kernel functions where random sampling is optimal?
Yeah.
I'm not sure.
So is this result tight, for example, in some cases that the best thing you can do is either do random sampling, or for example the best thing you can do is LSH?
Oh, I see. Are there situations where LSH actually doesn't help? So, as we'll see later, in some sense, how steep your kernel is, okay, is a very important factor. In some sense, the Gaussian is very steep, right? But you could think of kernel values that are even steeper than that. So definitely the structure of the structure of this kernel function does affect whether or not LSH is going to be useful at all. Because at some point you don't have locality sensitive hash functions that are able to distinguish between near and far points to the fidelity that you need. So yes, definitely you could construct kernels where random sampling is maybe the best that you could do.
Probably.
Maybe, I'll have to think about that. Intuitively it seems like it should be possible. Okay. Yes.
So you listed M and you did list beta. So somehow I'm guessing from that you're going to pay this factor of M in like oversampling or something, but you don't care that beta is it 1/2 or something else, or is it like for
I fix beta to be half. Okay. M is sort of this hidden factor which I didn't mention in this result. So
it will affect like the running time because you have to oversample or something.
M does affect the running time, yeah. But I've hidden it in the previous expression. So. Okay. Other questions? All right. Let me tell you about another piece. Yes.
Actually, I'll just ask a quick question about the kernel estimation. So usually, let's say in kernel density estimation, the kernel is not really fixed, right? In some sense, because you want to do model selection. You want to choose the bandwidth of the kernel. Let's say it's a Gaussian kernel, you want to choose the bandwidth of the kernel. And so would that mean here that within a model selection framework that you need to come up with a different hash function for every particular, or could you build a single data structure that, you see the question, right?
Yeah, I see. So, okay, this is a point that I didn't really address in this talk, but our work comes in at the point where you've fixed the kernel, where you've done your model selection already, and now you apply our data structure. So if you were actually going to not commit to the kernel, but you might pick from a variety of kernels, then you would actually need to design different data structures for different possible choices of the kernel. That's certainly one drawback of this approach. I will say, and maybe I'll comment on this later for some of the other work that I'll mention. Yeah.
So here the bad case is where the data has a very specific, like 2-point kind of form. If you have the promise that the data is not, that it's a bit more random.
Then you can actually get some improved results. Yeah. So if you make some assumptions that the data is pseudo-random in some sense, not all of it is concentrated in a small region, roughly speaking, and you quantify that in some way, then you can tie that into the analysis and get some improvement. Yeah. Okay. Other questions? All right. So let me tell you about another piece of work with Paris Similakis on what's called partition function estimation. Okay, so it's a very similar problem, slightly different. So let me tell you what the problem is. Again, you're given a bunch of points. You're given a function phi that takes inner products and maps them to a real number. You have a query y, which is also a unit vector. Okay, and now what we like to do is we like to take this query y and again sum up some pairwise function summed over the entire data set. But in this case, this pairwise function is exponential in some function of the inner product. Okay. That's what we like to do. And this is called the partition function. It's sort of a very interesting function. It arises in a number of different settings. People care about evaluating this quickly. We'll ask the same question. Can you design a data structure to pre-process the data set so as to compute this efficiently? Okay, to approximate this efficiency. All right. Okay, so let me say one thing about this before I start. Well, let's say that all of our results are going to be parameterized by how this function phi behaves. Okay, and the one thing that we need about this function phi is the Lipschitz constant. Okay, how fast this function phi changes. Let's say L of phi is the Lipschitz constant. Since this function phi is applied to inner products range between 1 and -1. These are unit vectors. Okay. We know that the maximum, the difference between the maximum value and minimum value is at most twice the Lipschitz constant. Okay? So we can normalize and make sure that all of the functions that we want, the kernel values, are all in this range e to the power of minus 2, L of phi, and 1, right, just by scaling. Okay, so let's say we're in that setting. And now, what we could do is, if our data set is very large, because all of our values are in this range, we could actually just random sample the data set and just pretend that we're going to compute everything on this random sample. So what I'm trying to say is that the effective n, the effective size of the data set, is actually e to the power of twice the Lipschitz constant. Right? If our data set was much larger than that, we could always sample down and bring it down to this size. Okay? So whenever I express my results as a function of L of phi, if you wanted to express them in terms of n, what you should do is you should take n to be e to the power of twice the Lipschitz constant. Okay? And similarly, mu, which is the average of this quantity, is some number between 1 over n and 1. Okay? All right. So we'll do this reduction beforehand. Okay, so here's the result. Basically, you should think of this result as an extension of the previous results, right, to a more general class of functions. Okay? So for any convex function phi, you can design a data structure where the query time is proportional to 1 over square root mu. Okay? And there's some dependence on this function phi. Now, this dependence on this function phi is a little ugly. I've sort of tried to hide it. There is this dependence here on the query time, and there is this dependence here on the preprocessing time. Okay? The reason I want to talk about this is mostly to highlight the techniques. I think the techniques are more interesting than the precise result itself. It just says that these hashing-based ideas can be applied more generally to a more general class of functions. Okay? It's not clear that this kind of dependence is necessarily the best possible, but it's sort of the techniques that I want to highlight more than this. Okay? I should say one more thing, which is the results on using locality sensitive hashing as a way to compute these estimates was actually independently done by Spring and Srivastav. And Anshumalli is here in the audience. And they were motivated by estimating exactly this kind of partition function. Okay, so they were trying to estimate this kind of partition function, and they realized that, it'd be nice to get some sort of importance sampling based estimator, and they used exactly locality sensitive hashing to compute this kind of thing. Okay, so you could say, what improvement do you get over random sampling? Roughly speaking, if you use this translation that n is e to the 2 of L of phi and mu is 1 over n, for random sampling you need space order of n, query time order of n. In our LSH-based estimator, you need space n to the 3 halves because you have a bunch of hash tables, but the query time becomes square root n. Okay, so you get a square root n improvement in the query time, roughly speaking. Okay. So let me tell you what's new in this data structure relative to what you've seen before. Okay. So earlier, we had one family of hash functions, and we built our hash tables using this one family of hash functions. In this, we're going to do something slightly different. We're going to have t different families of hash functions, h1 to ht. Okay, each of them is going to have their own collision probabilities. Okay, and in some sense, different hash families are going to be tailored to different portions of the inner product space. Okay, so different hash families are designed to have their collision probabilities peak for different values of inner products. Okay, so far when we've talked about locality sensitive hashing, I've talked about, implicitly you think about locality sensitive hashing where points that are nearby are more likely to hash onto the query bucket than points that are far away, right? Points that are close are more likely to collide than points that are far away. it's actually possible to tweak the idea of locality sensitive hashing a little bit and come up with this notion of distance sensitive hashing, where points that are at a certain distance, rather than points that are close by, points at a certain distance are more likely to collide than other points. So if you
to designing a new distance, just transforming the distance to a new distance and then doing LSH relative to the new distance function?
it's not quite as straightforward as that. I don't know how to do it in that way. Okay, but what this does is that if you look at the collision probability, you would assume that this is a monotone decreasing function, right? In this case, the collision probability is something that increases and then decreases and peaks exactly at some desired point in the inner product space. That's what it is. Okay. So we're going to choose a bunch of these different hash families, and each of them is designed to peak at a different point in our inner product space. Okay. Each of these is going to have their own collision probabilities in this way. Now, we actually want to compute this function, right, which is e to the power of some phi times the inner product. We're going to take this quantity and we're going to break it up over our t hash functions. And the tth hash function is going to be responsible for this one piece. Okay. So this is the quantity that we want to sum up. This is the quantity that we want to sum over the data set. We're going to break this up over our t hash functions. Okay. And the tth hash function is going to be responsible to sum up this quantity over the entire data set. Okay, that's what we're going to do. All right, so
what's the definition of WT?
Sorry?
What's the definition of WT?
So I didn't tell you what this WT is. I'll tell you how we get this WT. I'll sort of indicate that, but I won't give you very precise. So right now, let's just leave it as WT. We'll actually fix this later. Okay. All right, so in order to do this, we're going to do exactly what we did before. We're going to sample hash functions from each of these families, create these hash tables, pre-process the data set in this way. And then when the query comes along, we're going to also subject it to all of these hash functions, look at the query hash buckets, look at where the query hashes onto. And now, earlier, our hash function was exactly this quantity, right? We didn't actually sum up over the data set, over all of our t hash families. Now we're going to sum this up over all of our t hash families. Okay, that's what's going to happen, right? And the tth hash family is, remember, trying to compute the sum of these WT. Okay, so each one has their own weight function that they're trying to. Okay. So this seems like a horribly complicated scheme, right? There are too many moving parts. Right. You have these different hash families, then you have this complex estimator. The main challenge is how do you go about trying to get some grip on trying to analyze this, right? The main thing is trying to bound the variance of this overall estimator. Okay, so maybe I'll give you a flavor of how it's done, right? Of a sort of a cartoon version of how it's done, rather than really giving you any details. So, the main idea is that, look, earlier we said the key idea before was designing one hash family such that the collision probability was proportional to square root of the kernel value. Okay, this is actually a very hard thing to do in general. I mean, if you give me an arbitrary function e to the power of phi in a product of x and y, I don't know how to do this. Okay, in fact, I could do this exactly for this Gaussian, exponential, and polynomial families. I don't know how to do this for other ones. Okay. And so that's why we do this more complicated but more flexible scheme, which has the ability to handle way more functions. Okay. So as I said, we have this, let's say, is the function we're trying to estimate. We're going to break it up into a bunch of segments. Okay. Have a different hash function responsible for each segment. Okay. And sum up exactly this segment. Okay, so the tth hash function is going to be responsible for this segment. That's the picture that you should have in mind. It's not quite as clean. Actually, this tth hash function will be responsible for not just this segment, but something slightly wider than that. Okay. All right. So the main challenge is to figure out how do we decompose our function of interest into a bunch of different functions. Right? How do we compute these WTs? Exactly the question that Jairam was asking. Okay. So we're going to pick our hash families from these distance-sensitive hash functions that I mentioned before. Okay. And now, based on these collision probabilities, we're going to figure out what these weights should be. Okay. So our goal is to identify what these different hash families are. Each comes with their own collision probabilities, and then you need to figure out, for this particular hash family, what is the function that it's actually computing. Okay. And then this is the final estimator. Okay. So the key idea, and this is the key idea behind the analysis, is if we set our, so this is the function that we're trying to compute. We want to figure out what portion of this function should be allocated to the tth hash family. Okay. It turns out that if we allocate to the tth hash family this portion of this function, so what do we mean by this portion of this function? The portion that's allocated to the tth hash family is proportional to the square of the collision probability for the tth hash family. So if we make this choice, it turns out that there's a very nice simplification that happens in the analysis. Okay? The variance of this seemingly complicated scheme is somehow bounded by the variance of a much simpler scheme. Effectively, we can think of this as a simple hash function, one hash function, whose collision probability is the max of these collision probabilities. Okay, and this is a key simplification in the analysis. This makes our life much easier. Okay. So now our goal is to design these hash families such that the maximum of the collision probability behaves like square root of this particular function of the kind of estimate. Okay, and this is a much easier goal. This is exactly what we do. All right. Okay, I'll spare you much of the details. Let me tell you about, very quickly tell you about some of the other themes I wanted to touch on in the talk. So this is work that appeared at Fox 2018 with Artus Backers and Piotr Rendik in Paris. And this brings me back to this question that I mentioned before, which is, is this polynomial dependence on mu necessary? Okay. So there are actually lower bounds that are not exactly for the problem that we care about, but very similar problems that suggest that if your kernel is steep, if your kernel actually varies very rapidly, okay, and the Gaussian, for example, falls off very rapidly, then some sort of polynomial dependence on mu seems necessary. Okay. So if you want to get around this polynomial dependence on mu, you need some additional information about the kernel. So in particular, these kernels, it seems very difficult. Although we don't have a precise lower bound for our query problem, it seems difficult. It seems conceivable that it's not possible to do this for these kinds of kernels. But there are a bunch of other kernels that have polynomial dependence on distance. They vary more gracefully. They don't fall off as steeply. And for these, there's some hope that you might actually be able to get rid of this polynomial dependence on mu. Get a result where the query time is independent of mu, or behaves more gracefully with mu. Okay, and that's the main result. The main result is that this fast decay of kernel value is really the only obstruction to efficient algorithms. Okay, so if you had a kernel which decays more gracefully, then in fact you can get a better algorithm. Okay, and for this we actually parameterize the kernel. We say, okay, so we say the kernel is smooth if the following thing happens. Okay, if you look at the kernel value relative to x, look at a point z and look at a point y. Look at the ratio of their kernel values. Okay, so look at the kernel value of xz and xy and look at the ratio. If this depends on the ratio of distances raised to the power of t, okay, then we see that this kernel is LT smooth. Okay, so if you think about the kernel value as depending polynomially as a function of distances raised to the power of t, then we think of this function as smooth, okay, for a small value of t. And the point is, if your function is of this kind, then you can actually get a good result. Okay, so what's the result? The result says that if you have this problem where you have such a smooth kernel, okay, then you can do this in query time that depends essentially on 2 to the power of this t divided by epsilon squared, and the storage space is also 2 to the power of t times n. Okay, so somehow this, if you know that your kernel is smooth, then you can actually get a better result. Okay, so how does this work? I'll tell you the main idea, but maybe it'll be hard to express much more in 5 minutes. Okay, so suppose you have, let's go back to this idea that you had a bunch of weights, you want to sum up their values, right? And earlier we said that if you want to sum up these values, you can just sample one element, right, and look at the average. Now, if these values are all in a small range, if the ratio of the maximum to the minimum value is small, then you don't need to sample that many to get a good idea of what the average is. Okay? The main idea is to take your data set, right, and somehow partition them into pieces such that in each piece you have a bound on the ratio of the maximum to the minimum. Okay? So take your data set, partition into pieces such that in each piece there is a bound on the ratio of maximum to minimum. And now you can just go over all your pieces, and in each piece you won't have to sample very much to figure out what the contribution of that piece is. Right? That's the main idea. Yeah.
And so the number of pieces is exponential in t?
The number of pieces is exponential in t. Okay. What's the challenge in doing this? The challenge in doing this is that, again, these values are query dependent. This partition of the data set has to be somehow query dependent. It's not fixed, but somehow query dependent. Okay. But anyway, the point is we can handle all of this stuff, and we can actually design a data structure which at query time allows us to produce a partition in the data set where in each piece of our partition the ratio of the kernel values is small. Okay, and that's how this estimator works. Okay, I won't say very much about this analysis. It depends on a certain quantity called the averaged condition number, but I think at this point it will be very hard to since I'm out of time, I'm not going to explain what that quantity is. Okay. In the last few minutes, let me tell you about yet another piece of work where we used this idea of locality sensitive hashing as an important sampling facilitator. Okay, and this was work by with Carrie Wu and Vishnu Nachu, and this appeared at ICML 2018. So this is a slightly more practical paper. I'll tell you about the problem. I'll tell you what is different about what we did here relative to the other things that we've seen. Okay, that's the main thing I want to convey. Okay, so this was motivated by trying to design algorithms for what are called word embedding. So some of you might have heard about this thing. You have large corpuses of text. You take every word in this corpus and associate it with a high dimensional vector. Okay, and we asked the question, given such a collection of vectors, let's say they're all normalized with their unit vectors, given a query vector, can we tell how dense the region around this query vector is? Very simple question. Okay, so given this high dimensional data set, given a query vector, can we estimate how many points are in a nearby region around this query vector? Okay, and what does nearby mean? Let's say nearby is 60 degrees. Okay, let's just fix it to be 60 degrees for this purpose. So just to set the context, one particular data set that we were interested in is what's called this GLOVE data set. It consists of about 2,300,000 dimensional word vectors. Okay, and I said the range of interest is 0 to 60 degrees. Okay, now in this data set, most vectors are orthogonal. Right? So as you might expect, if you just pick random vectors which are 300 dimensional, you would expect most pairs of vectors to be orthogonal. In the 0 to 60 degree range, you do get interesting related things. So for example, if you try Venice, you'll get things like Florence and Naples and Rome. There are only 12 other word vectors which are in the 0 to 60 degree range. For a word like cake, you get shortcake, batter, tiramisu. There are about 117 such word vectors. For book, there are about 424 such word vectors. The point is, typically, there are very, very few points in your data set that are within 60 degrees, and they're quite correlated. Okay? So what we want to know is, how dense is this region? Given a query vector, how many points are within 60 degrees of the query vector? That's the question. Okay, so as you might expect, we applied this locality sensitive hashing based technique. The natural LSH here to use is this random hyperplane based LSH. Slice the space of a random hyperplane, assign 1 bit based on which side of the hyperplane you fall on, right? We had about 2 million data points. We used 20-bit hash addresses, which means on average you expect about 2 points to fall into a hash bucket. Okay, what's the problem? If you apply a vanilla LSH, right, in order to estimate how many things are within 60 degrees, you would need a lot of hash tables. Okay, and the main point is that look at two vectors that are 60 degrees from each other. Apply 20 different hash functions. What's the probability that they fall into the same hash bucket? What is the probability that they fall on the same side of these 20 different hyperplanes? It's very, very small. Okay, so in order to even see something of interest in the 0 to 60 range, you would need a lot of different hash tables. Okay, and that's a big problem. Okay, so we modified this scheme, and this is the key innovation in this paper. We said, instead of sampling from the hash bucket that the query falls into, we sample from all the hash buckets that are within a certain Hamming radius of this query. Okay.
Isn't this like multi-probe hashing or multi-probe LSH?
It is related, yes. It is related. So in multi-probe LSH, what happens is, in addition to the query bucket, you also probe a bunch of other buckets that you think are likely to contain things that are nearby. Very similar idea. Okay. There are some issues with using exactly that, which is why we did this. Okay. So we sample from everything within a Hamming distance T from the query bucket. Okay. One key improvement is that in all of the previous schemes that I described, you basically pick one sample per hash bucket. And so in some sense, in the analysis, you need this. Otherwise, there are dependencies that you can't control and can't get rid of. Here, we did actually try to get, it was very important for us to get multiple samples per hash table. We wanted to control the number of hash tables. Okay. So, okay,
Maybe I'm missing something simple here, which is, I mean, for the standard research, you just need to detect collision, right?
Yes.
But in terms of the data structure that would implement this, detecting all things that are at distance at most t, how would you would you scan through all the cells?
What would you report?
Yes,
actually?
yes.
What number would you report?
Sorry?
How do you get to the output, like 400 or something from this?
Yeah. So, okay. How do we sample, right? That's the question. You don't want to actually examine all the buckets in this particular Hamming radius, okay? So imagine you have this 20-bit hash table, right, which has 2 to the 20 entries. You know the query falls into one bucket. I want to pick a random element from amongst all buckets that are within Hamming radius 5 of this. How do I do that? I don't want to go over all the 20 choose 5 different Hamming buckets. Okay. Turns out that you can actually pre-process. Okay, so you can pre-process this hash table to have some additional information that allows you to random sample. Okay. So this is a slightly subtle point, but you can work this out. It's not very hard. Yeah.
Yeah, but how do you eventually like estimate the number, like this 400 or something that you mentioned? Like you get a sample from nearby.
Okay. So what do you do?
Right. To what you said, which is your goal, which was to estimate.
Okay. Good. So you use the same the importance sampling machinery, right? So given an element, first of all, if it's not within the 0 to 60 range, it counts as 0. Right? If it's within the 0 to 60 range, it has a weight of 1, but divided by the probability that you would have seen this element in the range of interest. And now you average this over a bunch.
Like 0, 1,
10. Yeah. Okay. All right. So there are. I'm over time. I should stop. This is my last slide. There are there are two sources of error. Okay. One issue is if you have too few hash tables, then you have some error baked into your estimates. No matter how many samples you take, you're never going to get better than whatever this baked-in error is. Right? So you have to make sure that you have enough hash tables. And then, of course, you have to make sure you have enough samples. And these are two different issues. So it turns out that the following thing happens. If you compute the minimum probability that an element of interest falls into your sampling pool, right? Earlier, our sampling pool was just the bucket that the query falls into. That was too small. The probability that an element of interest falls into that was too small. That's why we needed a lot of hash tables. The whole point of expanding the sampling pool is to increase this probability. And so the number of hash tables that we need is actually much lower, turns out. And now, what's the number of samples that we need? Well, this is some sort of data-dependent quantity. Okay, so after we expand our sampling pool, now we ask the question, in this sampling pool, what's the expected fraction of elements of interest, right? 1 over that is the number of samples that we need. Okay. So in worst case, this could be pretty bad, but this works well in practice. And so this is sort of a data-dependent guarantee. It's hard to get a worst case guarantee. All right, good. I'll stop here. I just want to give you a flavor of some of the ideas that are involved in all these different pieces of work and try to bring out maybe some of the key differences. Lots of interesting applications of LSH. I think what's interesting is that LSH has been around for a long time, but thinking about it as an important sampling facilitator has led to new insights, and hopefully some of you will be motivated to take some of these directions even further. So thank you.
So in the interest of time, we'll just leave any further questions that you can ask Moses offline. The next one will be at 11, and until then we have a break.
Sorry.